All right, thank you everyone for coming to this session. So today we'll be talking about optimization and performance tuning techniques with the Apache Spark engine in a Delta Lakehouse environment, or from the Delta Lakehouse perspective. Just a quick introduction to who I am. My name is Johan Hille Bringsdal. I'm originally from Norway, but been living in Copenhagen for the last 21 years. I have a software design master's degree from the IT University of Copenhagen. And my current title is Senior Business Analytics Consultant for a company called Today and their Data and AI department. But you can just call me a data engineer. Me personally, I've worked with primarily the Microsoft Azure platform and a lot of the different things that fall under those wings. Primarily inside of Azure Synapse Analytics, which is sort of the older version of Microsoft Fabric. Then also Microsoft Fabric when it came out. But primarily it's been within Databricks and trying to tune larger data sources. The commonality between the last three is that they all run on Apache Spark, at least when you're trying to process your data, and they're all storing data inside of the Delta Lake. And personally, some of the projects that I've been working with, I have worked on tables that contain over 50 billion rows of data and trying to figure out the best way to performance tune and optimize that so that you get fast run times. So let's just quickly go through the agenda for today. First of all, I'm going to talk about what is Apache Spark, the engine itself, and then also briefly, what is the Delta Lakehouse, where we're actually storing the data that Apache Spark is processing. Then I'll look some more details into the cluster architecture, so the actual clusters that are running with Apache Spark. We'll take a look at some transformation examples, digging into inside of the engine, what's happening behind the scenes when you're throwing a query at Apache Spark. Then we'll look at the actual brain of a Spark, which is the Spark Catalyst Optimizer, and how that works with optimizing your queries. Then some information on the Delta Lakehouse and Delta tables in specific. What are Delta tables? How you write data with Spark to these tables, some data maintenance techniques, so how to make sure that your storage isn't getting out of hand, and then some common storage pitfalls that people fall into usually, and lastly, some optimization techniques that I myself have used when working with these massive data sources. So just briefly, a disclaimer. There is no one-size-fit-all when you're working with Apache clusters. These are usually just general guidelines on how you can approach it. But all solutions require a unique approach when you're actually working with different data sources. So these are some things you can keep in mind when you're actually working with your data. So what's Apache Spark? Apache Spark is an open-source distributed framework which is built for handling large-scale data with speed and efficiency. It's sort of a modern ETL engine, similar to what we've seen on older solutions. So it's an extract, transformation, and load engine, which speeds up your data workflow with an in-memory processing, taking advantage of in-memory processing. It's developed by the team that also has Databricks, which is a platform as a service, which is primarily where I have been working in notebooks, writing in Python or PySpark. And they have a lot of initially proprietary features, but they usually tend to become generally available later on. So one of the key advantages of using the Apache Spark engine. Number one, speed. You have in-memory processing, which reduces your overall I/O. Then you have versatility, because you can use both batch and streaming. So you can have one batch a day, or you can have almost close to live data streaming with real-time queries. And lastly, you have scalability. You can have a single node working with your processing of data, but you can also scale all the way up to 1,000+ nodes if you have very, very large amounts of data, where you can handle up to petabyte size files. So now that we have looked at what's the engine that's processing the data, what is a Delta Lakehouse? So it's important to note here that just because we're using the Delta Lakehouse in these examples, it doesn't mean that older versions of data warehousing or Delta Lakes are invalid approaches. This just has some features that are beneficial to the way that you process your data and store your data. So there has been a lot of technological advancements in how you handle OLAP workloads over time. With data warehousing, you're quite limited to structured data. There's quite a high cost for scaling, whether you're having an on-prem service or in the cloud. And it lacks some flexibilities when it comes to real-time data and very big data processing. The Delta Lake lacks consistency in terms of no ACID transactions that we also know from the data warehousing. It has slow performance because it does not have the same type of optimization, and it's quite difficult to manage data quality and governance. So then we come to the Delta Lakehouse, which is where we would want to store our data using the Apache Spark engine. Here we actually combine structure and flexibility for all kinds of data types. It does support ACID transactions, so when you're writing to your table, it either completely happens or not at all. And it's optimized for both high-performance analytics and real-time processing. So now we know the engine, Apache Spark, and we know where we want to store our data. So let's take a look specifically at the cluster architecture inside of the Spark engine. So here's a very simple example. This is a 3-node cluster. It's quite a small cluster. We have a driver node on the left, and we have 2 worker nodes. And inside of those 2 worker nodes, we have 2 cores each. The driver node is responsible for assigning the tasks that come in when you're actually throwing a query at it. The worker nodes are the ones that's hosting these executors to perform the tasks, and the core itself is the one that's actually doing the work. When you're working with a cluster like this, there are 2 main types of data transformations that happen. Number 1 is a narrow transformation. What that means is it's an independent partition processing where no data shuffling happens, meaning that the driver node assigns a partition to a specific core, and that core is able to finish that task without sharing any information between the other cores. So it's able to complete its task, send it back to the driver, and send an output to the client. That could be functions such as a map function, filter function, or a union function. Then we have a wide transformation, which is the opposite. This is the case where you do have data shuffling, meaning that a core does need information from some of the other cores in order to finish the task. That could be something like a group by, a join, or an aggregate function. Now, it's very difficult in modern solutions to have to avoid the wide transformations. They're not necessarily bad. You just want to know how to actually approach them and optimize them. This is an example from the Databricks interface where you are actually creating your own cluster. This would be similar on any other platform where we're working with clusters. So first of all, you want to choose your worker types. You have your cores, which is the one in red that we saw on the previous slide. And here you want to decide the number of CPUs or cores per worker to try to optimize your parallel processing power. So essentially, it's the width of the cluster. How many cores do you have working at the same time? The other option you want to choose is the gigabyte of RAM, so the size of each cluster. And that would then equal the height of the cluster. So you're thinking about width and height. You also have the option here to choose a min and a max so that you can auto-scale your solutions. So that if you have differing workloads, you can have a cluster that scales up really large, or you can have one that stays at a single node. Also, inside of Databricks, which is similar to many other places, you have these things called runtime versions. What that basically does is that it bundles the versioning number of a specific programming language together to make sure that there are no breaking changes in between them. So you keep a Spark version, you have a Delta version, and a Python version, etc., to make sure that it's compatible together. One last little anecdote here is in Databricks, they have a feature that was released in July called a serverless cluster. And basically what that means is you don't actually need to set up anything yourself. You can just throw a query at what they're calling a serverless cluster that they will have available at all times. I wrote to be careful because when you throw that query at the cluster, it'll scale up depending on what it needs. So if it identifies that it's a very complex cluster or a query, it'll scale up essentially forever. So if you write bad code, this can be really expensive. So one extremely simple example of how task execution work inside of a Spark cluster. In this example, we want to run a code where we say Spark SQL select star from our sales table. Now this sales table happens to be a 625 megabyte file, just one. Now, as a rule of thumb here, Spark wants to split your memory partitions into equally sized memory partitions, and it wants to keep them at a roughly 128 megabytes each. That is simply a default value set by Spark. You can change this yourself, but that's just the default. So with a 625 megabyte file, that becomes 5 memory partitions. At the bottom of the screen, you can see a cluster here where we have a driver, we have 4 workers, and all of these workers have 2 cores each. But we only have 5 memory partitions, but we have 8 workers in total. So as you can see, those that are marked green, those are the ones that are actually working on a task, but the 3 gray ones are idling, meaning they're actually not doing anything. So now I'm going to go through in depth a narrow transformation example. So the one we talked about before, where you do not need any data shuffling in between each query. So in this case, we want to use an example where we have a cluster that is 1 driver, 6 workers, where each worker has 2 cores each. The scenario that we want to succeed with is we have a data set called cars, and we want to filter out every blue car from this data set. So it's quite a simple example, but it's interesting to see how it works. So first of all, the Spark engine splits it into equally sized memory partitions, and you can see those on the top left here. So the driver says we need to filter out all the blue cars from this data set and return a data frame. So it tells each core to go and work on one of these memory partitions. The cores will then go up and pick a memory partition and start working on it. But as you can see here, every single core is working on a specific memory partition, but we still have 4 memories left. So these are not actually being worked on right now because every single core is occupied. So now it asks to do the actual task. Some of the memory partitions might be more complex than others, so some finish early and return that information back to the driver. Now the main issue here is these are finished, these four black cores, but they cannot start with the next memory partition because there is still a core inside of their worker that is working, so they cannot actually start on a new one. Then the next set completes, returns to the driver, and then the 4 can actually go back and start working on the next 4 memory partitions. And we continue. These 4 also finish, return to the driver, and then we're finished with that. There was no data shuffling required in between these cores. They only had to actually filter out the blue cars from each individual memory partition and return that to the driver. So that was a narrow transformation example. Now let's take a look at a wide transformation example where we do need data shuffling. Again, this is quite a simple example, but it shows exactly how it works. Again, we have the dataset cars, and this time we want to group by color and then do a count to identify how many of each car color is there. This time, we only have 4 memory partitions, but we have the same sized cluster. So we have 4 cores that go and work with each memory partition. These memories will then start working, and when they're done counting inside of each memory partition, that information is written to disk. So it's doing a shuffle write, so that information is shared across. And when it's done, that is then returned to the driver as information, and we've done with the partial count, which is the stage 1, the local count it's called. When we're done with stage 1, we're starting stage 2. And stage 2 is the global count. So now we have the information of each individual group count inside of the disk, and we do then a shuffle read information, and it's given to the G core over here, and that is then able to simply just do a final merge count where you have the total count of each car. And that information is sent back to the driver. So that was 2 very simple examples of how it works. Now, this is a little bit more complex. This is what's called the Spark Catalyst Optimizer, and that is essentially the brain of how Spark works. What happens here is that whenever you throw any kind of query at Spark, it is transforming that query into what's called an abstract syntax tree, the one you can see here on the left. Basically, it's taking a tree form with nodes where every single node is one operation that's happening inside of your query. It could be a select statement, a where statement, a filter, something like that. Then it sends it through the tree or through the Catalyst Optimizer, identifying if the schema is correct, analyzing the data types. Then it's creating multiple physical plans, as it's calling it, and then it does this cost-based optimization analysis to identify which of these physical plans is actually the one that is the least expensive for us when we want to return that data to the client. The Catalyst Optimizer does many, many things underneath the hood, but I want to highlight 4 main things that it does, which is really important to know. So what does it actually optimize in the query? Number 1 is it does something called predicate pushdown. Predicate pushdown is actually where it takes the filter that you have on your data and pushes as close to the source as possible so that you only read the required amount of data. It does something called constant folding, so that if you have a constant calculation inside of your query, that will then just be pre-computed once and sent into a abstract tree node itself. It does something called projection pruning, where it identifies which columns from your data set that you need, and everything else is completely ignored, also leaving less memory or using up less memory. And the last one I want to highlight is join reordering. So if you have a complex join and you have joined it in a specific way in your query, the Spark is actually able to identify if you can order that in a better way to make sure that you don't have too many unnecessary rows joined together. So I want to go through just a quick example of each of these, how it looks in a code example. So here for the predicate pushdown, we're reading into a data frame a table called products. Then on the next line of code, we want to filter that data frame on the column called category is equal to electronics. What Spark is smart enough to do here is it pushes the filter that happens on line 2 up to line 1, meaning that we're actually never reading anything other than the category and the electronics data from that data set. And thus we're reducing the I/O significantly. The next example here is constant folding. This is quite a simple example, but in this here, we're reading some results and we want to do a score column, total score column. And what happens here is we have the 10 minus 3 at the end. Now that's a constant, happens every single time, so it's able to just identify that it's just 7, and that 7 is returned inside of one of these nodes in the abstract syntax tree, and it knows through the entire query that this is just 7. Then it does projection pruning. So here we want to select a specific column. So we're selecting the product ID and the price column, but we're also still filtering on the category. So that means that the Spark Catalyst Optimizer is able to identify we don't need any other columns than the product ID and the price, but also the category column because we're filtering on it. So all other columns are ignored. And here, join reordering, as I talked about, we have 3 tables joining them together. We have written it in a specific way, but Spark is able to identify, is there a better way to do this? And thus it actually shuffles it around if it can find one. Some final words on the optimizer. There are many ways of writing your code inside of these notebooks. Like myself personally, I've used Databricks and I've used Microsoft Fabric, and here you have both Spark SQL, Python, R, and Scala available. And there has been a lot of concerns, like which language should I choose? Does it actually affect your performance? But as a matter of fact, it doesn't affect your performance because the language, no matter what, the query is then translated into these logical plans underneath the hood, and it's going to be in the same format no matter what. There is, however, one exception, and that is if you're using user-defined functions or UDFs, because UDFs is a black box for Spark. It's unable to actually handle that in the same way as it would with regular queries. So it actually has to serialize and deserialize it between where the compute happens every single time that it's running that code. Again, one tiny exception. If you write your UDFs in Scala, it's actually able to do the compute inside of the engine. So that's just a little caveat there. Inside of your notebooks, you would then store the data sort of in an abstraction layer here, and this is where we then use data frames. Data frames is where you can have it in a tabular format, so tables. And the Spark Catalyst Optimizer is using the data frame API whenever it's doing its optimization. The RDDs is sort of an older version of that, and if you're using RDDs, the Spark Catalyst Optimizer is not applying its optimization techniques. It's still possible, but you do have to write every single code that does that optimization yourself, making it a lot more complex. So that's why we want to use the data frame API. So now we've looked at the engine, and we've looked at exactly how it works under the hood. But where do we actually store our data? We store it inside a Delta Lakehouse and inside of what we call Delta tables. So what is a Delta table? A Delta table is a data storage format which is built on top of any data lake, which could be Azure Data Lake Storage, it could be Amazon S3, it could be Google Cloud Storage, and it puts it inside immutable Parquet files. It has ACID transactions, meaning atomicity, consistency, isolation, and durability, just like data warehousing with, for example, a SQL server database. It has schema enforcement, which we've seen before, but it also has schema evolution, meaning that if you have data that is changing over time, you can allow schema evolution inside of your delta tables so that if a new column is applied to your table, that column will simply just be appended to the existing table and just be nulled for every single record that existed prior to that. It has versioning of data, which allows us for something called time travel, so that if you have made a mistake or for some other reason you need to access a previous version of your table, you can simply say select as of version 5, and then you can go back to a previous version. It has efficient data management and optimization with everything we just talked about. So it supports compaction, caching, clustering, basically giving us faster reads and writes. So let's take a look at what a delta table actually looks like. So with this screenshot, that's just a random delta table where you have the Parquet files stored underneath this delta log. The delta log is also called the transaction log, and this is essentially the entire heart of the delta table where everything important is stored. Not the actual data, but all the metadata information. So the transaction log is the key mechanism that enables all these Delta Lake features to happen. It tracks every single action on the table, so every single insert and delete operation that you do is kept in this in a JSON file that is versioned by numbering. So you can also see previous versions of that. It stores schema information, partition data, and file statistics such as the minimum and maximum value for the different numeric columns, and that gives you efficient query optimization. This delta log folder is used by the Catalyst optimizer to selectively read only the relevant data, so these 4 examples we looked at before, which significantly improves your query performance whenever you're reading from the table. So data pruning, partition pruning, and file skipping. And just an important note is that you should never ever manually delete anything from the delta table, because if you were to go into the folder yourself, delete a Parquet file, the delta log does not register that you have deleted this Parquet file. So you're actually just breaking your table as a whole. So make sure that you only do operations logically. So how do we actually write data to these delta tables? So here are just 3 examples of how you can add data to your delta tables using Spark. Number 1 is the overwrite function. Basically, you have a batch of data coming in, and you're taking that batch and you're overriding the existing contents of your delta table with what is in the new batch. The files that are present in your table are not actually removed physically, they're just marked as being logically deleted. So if you were to query a table after an overwrite, you will only get the contents of that last batch of data. Then you have an append. Append is essentially you're taking your existing data, and then you're just adding whatever the batch contained whenever you're adding that data. So you're adding a new version to your table inside of this transaction log we just looked at before, and that version is just your existing data plus the appended data. And lastly, we have an update statement. Here you're actually going in, identifying rows that you want to change based on maybe something changed in your data source. And it identifies which rows in which Parquet files needs to be updated. It takes that entire Parquet file because remember, it's immutable. So it rewrites the entire file, puts the new information in a new file, and the old one is then marked as logically deleted. Again, not removed physically. Here's a very simple example of how it works. So in version 0 on the left, we're creating our table. Here we're adding file A. So now our entire table consists of file A. In version 1, we're appending, meaning we're adding file B. So the entire contents of the table is now file A and file B. In version 2, we do an overwrite. So we're adding file C, but we're logically removing file A and file B. So if you're trying to read your table now, the information in those files will not be there. And this is where you can use the time travel functionality. So if you want to go back to version 1, where file C is not present, you can do that. File C is still physically in the table, but you can read from older versions. So it's logically able to distinguish between the files like that. And just very briefly, how we want to structure our data when we're looking at a lake or a Delta Lake house. This is what's called a medallion structure. There's many different ways of doing this. Some people add more layers than this, so this is just one example. But essentially, you have delta tables in your bronze layer, which is just pure raw data, untouched. Then you have the silver layer where you clean your data up and you maybe split it out into different entities. And this is something maybe data scientists can start using data. And lastly, you have this enriched layer or the gold layer where your data is specifically curated for the need of the BI consumers or machine learning consumers. So now we're appending a lot of data, we're overriding some data, and as I mentioned, none of the files are actually being removed. So what do we do with all these extra Parquet files, the older versions of the Parquet files? Because they're just there and they're taking up storage. With the Apache Spark engine, we have two maintenance techniques called the optimize function and the vacuum function, which is there to help you with your storage. So let's take a look at an example with optimize. Here's a screenshot of again, a random Delta table, which has many Parquet files at a roughly 7.8 megabyte size, and then a single big one, which is like an historical append that was done. And what we want to do is all these files together, that is the version of the Delta table as is right now. But we want to make sure that these are compacted into fewer files at a larger size. So we're running the optimize command on this table. When we do that, we're adding one new file to the table, which is a 242 megabyte file, but that file alone contains the entire content of your Delta table. So all the other ones that you see are now marked as logically deleted. You can't see that here, but you will be able to reference that in the Delta log. But now we're just adding more files. We still have a lot of old files. Same here. This is an example on a bigger table where we have a lot of 266 megabyte files and one 4 gigabyte historical append. And just as a rule of thumb, Spark tries to aim at having Parquet files at a maximum size of 1 gigabyte. So after running the optimize command on a bigger table like this, it ends up having 4 bigger size files, around 900 megabytes each, which then those 4 together contains your entire data set. But as I said, now we have a lot of extra files. We're simply just adding more files. What about storage? So this is where the vacuum command comes in. The vacuum command goes in and simply removes physically, this time we physically remove all the files that have been marked as deleted from previous operations. So if we did an optimize, all these are marked as deleted, and we want to clean that up. Now, there is a default retention period so that you don't accidentally remove versions that you want to keep for later. So basically, just for this example's purpose, I did something called a force vacuum, where I'm ignoring the retention period just to show how it would clean up. So assuming no new data came in after running a vacuum, we actually remove physically all these files from the Delta table, and we're just left with that 242 megabyte file that we looked at before after running the optimize command. So now we've cleaned our storage, and we have one file which is optimized for read queries. So there are still some common pitfalls that people fall into without using the two functions that we talked about before. One of them is the tiny files problem, and another is over-partitioning. So if we're looking at the tiny files problem, especially when we're using Spark, it's very common that it happens whenever we're doing micro-batching or streaming of data, so structured streaming. Because this time you might have data coming into your table every 5 seconds or every 1 minute. And the amount of data that's come in since last time might be very small, and it has to rewrite a new file. So that might be a very small sized file. And this is where you can actually fix that with running an optimize, maybe once a night, or maybe once an hour, depending on the amount of data coming in, and that would then compact a lot of your files. There are functions in newer versions of Spark that actually has some kind of auto-optimize or write-optimize functionality so that it happens more dynamically. But if you want to make sure that it runs properly, I'd still suggest running some optimize functions. Then you have over-partitioning from a Hive partitioning perspective. Now, this can work if you know your data well, but if you haven't sorted your data previously and just put it into a bunch of different partitions, as in folders inside of your lake, you end up having to scan a bunch of different directories. And if you do this, let's say over a year, where you have year, month, day, and maybe even hour as well, you would end up with several thousand directories over a year, which could be difficult to scan through. The rule of thumb from at least Delta's side is if you have a Delta table that is below 1 terabyte in total, don't do any partitioning. But there are, of course, exceptions to this if you know your data well and you're able to sort it correctly. So, Just briefly, I want to talk about some optimization techniques that I myself have used whenever I've worked on bigger projects with billions of rows of data. It's something that reduces the scan time and gives the catalyst more metadata information or better metadata information to use whenever it is optimizing your data. First one is something called liquid clustering. What liquid clustering does is it's the best method for data skipping, first of all. And it actually takes the data inside of your table and groups it into to be closer together physically, so that when you read, the Catalyst optimizer knows that at some point it doesn't have to look any further because it knows exactly what it's looking for. It reduces your metadata overhead, and it creates a flexible file structure that adapts the file sizes individually and the counts inside of your metadata to relevance and the query frequency that you have on your table. There are some limitations, and there is a maximum 4 columns that you can cluster by. It has something called eager clustering, meaning that if you have, first of all, I forgot to mention that when you create your delta table, you want to cluster by a certain set of columns so that that clustering is applied to your table going forward. It has something called eager clustering. So if you're appending data to a table that has added liquid clustering, it will, every time you run an optimize later on, it will then fit that appended data into your existing clusters. But if your appends are bigger than 512 gigabyte, which is quite a lot of data, that would not work. And it's generally available in Delta 3.1 and above, outside the Databricks, because it used to be a Databricks only functionality. Here's a quick picture of how it looks inside the files themselves. So this is your Delta table. This is an example where we have applied liquid clustering on the customer column and the year column. And it splits the data into these chunks or partitions where you're essentially saying the enterprise customers are more frequently accessed whenever we read, so that they are then spaced into smaller partitions. But these tiny customers here in 2023, 2022, they're very, very rarely used, so we want to just keep that in a bigger partition. And that is the logic that is applied whenever you're doing your liquid clustering. And as I said, you can do up to 4 columns like this. The next one, optimization technique, is something called a deletion vector. And deletion vectors are really good if you're having frequent changes to your data set. And that goes back to the fact that your Parquet files are immutable. So if you have a delete statement or an update statement or a merge statement to your table, normally it would require to identify which Parquet file contains the row they want to change, take the contents of it, rewrite the entire thing, mark the old one as deleted. That's normally how it would work. With deletion vectors, all your deletes, updates, and merges are actually stored inside of separate files inside of your Delta table. These files are called deletion vectors, and they're stored there. What that means, it's introducing something called merge on read, which basically when you're reading from a data set that has deletion vectors enabled, it is able to identify what has been deleted or has been changed. We're not actually rewriting the files. The rows are still there, but when we do the read, you're merging the existing data together with these deletion vector files that are at the bottom of your Delta table, and they're able to identify the rows that have been deleted, and then those will then be filtered out when you're actually showing your data through the read. So it works sort of as a soft delete option. When you run an optimize function, the one we talked about before, on a table that contains deletion vectors, then you do the rewriting of the files. Because obviously, if you just keep deletion vectors there forever, you're going to end up with a bunch of extra files in your table, which is just going to cause a lot of extra storage. So at some point, you still want to do that, which is why it's usually said that performance with a deletion vector enabled is usually called, it's an amortized cost, because you're not doing it right now, but you're doing it later. And that's a very good example if you have streaming data where you're using micro-batching, and every single time that you do a micro-batch, you're updating some records or you're deleting some records. If you had to do that rewriting of these big Parquet files every single time that you have to do an update statement, that would interfere with your performance. So you're doing that as that you're only adding that information to new deletion vector files and then handling that performance later on when you're doing your optimize. For example, in a nightly load. Here's a simple picture of how it actually looks. On the left, we have snapshot 2. So the Parquet file number 7 contains a certain amount of data. We do a delete statement on that table. The file itself is the same. We're simply just adding an additional file at the bottom that says, this is the deletion vector file. Now, file 7 has position 4 and 5 deleted. So we now know that going forward whenever we query the data set. So that was a lot of information. So there are some key takeaways here. Number one, I'd say know your data. Identify the kind of cluster size that you need whenever you're transforming or processing data from your data source. You want to know whether you want a wide or a tall cluster. So we want to parallelize a lot, which can be a problem if you're having a lot of data shuffling, or do you want larger megabyte or larger gigabyte cluster sizes or core sizes? You want to be able to control the number of files and reduce the I/O in your table as much as possible by using optimize and vacuum for your Delta tables. And then you want to take advantage of all the functionalities that the Spark Catalyst Optimizer is doing or applying for you whenever you're running your queries using Spark. And in that way, you can performance tune a lot when you're especially using very large tables where performance can be a real big issue. Because the easy choice, which a lot of people do, is they're encountering a very, very large data set. And the easy choice, just increase the size of your cluster. But when you increase the size of your cluster, you're also going to get a much larger bill at the end of the month. So the best approach here is to look at your data, find out how can you actually performance tune it by looking into all these different techniques. And then you can keep your cluster size a lot smaller than what people think. There is a lot of clusters or a lot of queries that you can run on single node clusters without actually knowing it. And people just thinking, we'll just pick a medium cluster because that sounds default. So you can save a lot of costs by actually looking into these performance tuning techniques. So that was actually it for today. So if there was any questions. So you're writing from what to what, sorry?
Parquet files. You're doing, well, okay. We're reading in Parquet files. We're doing transformations on the data, and then we're storing it into MS SQL.
But you're using Apache Spark as the processing tool?
Yeah,
Okay.
Spark and notebooks.
Yeah, so I would assume that you can apply some techniques when you're doing the read. So when you're doing the transformation inside of the notebook, you're applying it there. But in terms of storage, I'm not entirely sure how that would work. Yeah, we have someone else who can answer the question. Yeah.
My recommendation when storing to SQL servers is not on the Spark part, but it's on the SQL Server part, making sure that you're storing into heaps the tables without indexes, because that's the fastest write. You can't utilize the what's called parallelism when writing to a SQL server. Exactly. So the fastest part is to write to a heap and then apply your index. Yeah.
Yeah. Any other questions? All right. Oh, there's one here. Data quality?
Yeah, how would you audit and do like write, audit, publish with your Spark?
Yeah, so the data quality usually we handle through this medallion architecture. So we keeping the data delta table wise, we're storing it in this raw format, making sure that that is just exactly how our data source looks. Then we have some transformation logic between the raw layer and this silver layer, where we then make sure that the data quality is up to whatever standards we want. So you have to apply some kind of logic, of course, some testing, unit testing on your data to make sure that it's the correct data types, etc. And then you can move that data after it's been sort of quality tested in the silver layer onto your gold layer, making sure that the gold layer is signed off the data quality wise to the BI and the machine learning data where it needs to be used. I hope that answered your question. Yeah. Yeah. We have used, I have personally tried to use Great Expectations before, yeah, where we have sort of testing on the contents of the data. That is something you can do as well. I've not used it a lot, but I have tested it out. So with yeah, but it's a good idea to use that. But there are a lot of other tools that you can also use. I can't remember the library name at the top of my head, but yeah, Soda Core is one that you can use for data quality checks whenever you're make sure that your data actually is up to standard. Yep. All right. Thank you very much.